Hello friends, in the last class we discussed in detail about Gauss's law of electrostatics. So the Gauss's law of electrostatics can be stated as integral E dot dA is equal to Q over epsilon 0. So this Q is the enclosed charge. Gaussian surface we also discussed that is an imaginary closed surface. So the electric flux is always equivalent to the charge enclosed within the closed surface. So this is the summary of the Gauss's law. And this law is very much useful in calculating what? Electric field. So using Gauss's law, we can determine the electric field very easily, provided there is a lot of symmetry. The charge is symmetrically distributed, the electric field is uniform. So if you have all these conditions satisfied, then we can easily construct a Gaussian surface and then we can evaluate the electric field. Now in this particular video we are going to look into three specific cases where we are going to evaluate the electric field in the context of a spherical symmetry. Then we are going to consider planar symmetry. Then we are going to consider line of symmetry or linear symmetry. So first, let us discuss the spherical symmetry. So let's get on with this example. Suppose you have a sphere and the radius of this particular sphere is, let us say, capital R, and let's say that this particular sphere is charged uniformly on its surface with a positive charge Q. Now we would like to calculate the electric field, the value of the electric field for R lesser than R, that is at a point having a radius R which is lesser than R, and then at a point having a radius R greater than R. So let's take a particular point which is outside this particular sphere. So we just want to calculate what is going to be the charge distribution at this particular point. Now we have to first see whether we can construct a Gaussian surface. Yes, of course we can construct a Gaussian surface. So we can draw another sphere, and let's say that this radius is small r. Now we just want to calculate what is going to be the electric field over here. So this is our Gaussian surface. Okay. Now we know what Gauss theorem is. So this is integral E dot dA is equal to the enclosed charge divided by epsilon 0. So that's the Gauss's law for you. So let's get started by evaluating the left hand side first. So the left hand side is E dot dA. Now since this particular surface is uniformly charged, so let's say that the charge is concentrated at this particular point. Then you know how the electric field lines proceed. They start from the positive charge in this fashion. So it points outward from the positive charge. So let's map the electric field lines first. So this is the way it looks like. Now this is the direction of your electric field. In other words, the electric field is radially pointing outwards. So it is radial, it's radially pointing outwards, and electric field is uniform, so electric field can be taken, outside the purview of the integral. Now we just have dA. Now what is dA? dA is nothing but the surface area of the sphere. So this is very simple for us to evaluate. So the left hand side has been evaluated to E equals 4 pi r square. Now this right hand side is, it's very simple. It's once again, so let's put it like this. So this is E dot dA. This is your left hand side. As far as the right hand side is concerned, the charge enclosed is nothing but the positive charge itself over epsilon 0. So the electric field is very straightforward. This is equal to Q over 4 pi epsilon 0 r square. So this is the value of the electric field outside at a point, at an arbitrary point. This is the value of the electric field when you have what can I say, spherical symmetry. Now things can get a little bit trickier. How it can get a little bit trickier we shall see. Now suppose you want to evaluate, this is already over, r is greater than r. Suppose you want to evaluate this particular thing, r is lesser than r. So you just need to construct another Gaussian surface like this. So once again, let's assume that this radius is r. Now the evaluation of electric field is once again the same. So we need not do the left hand side once again. So it's pretty straightforward. The left hand side is E dot dA. It's one and the same. It's going to be 4 pi r square. But however, the charge enclosed is a little bit tricky. So the charge enclosed over epsilon 0. The enclosed charge is, what can I say, q times r cube over r cube. So how this comes about? The volume of this small sphere is 4 by 3 pi r cube. The volume of this particular sphere is 4 by 3 pi capital R cube. Now this first Gaussian surface, so this is your first Gaussian surface, or the inner Gaussian surface, so we'll call this as inner Gaussian surface, GS for Gaussian surface. Now this, what can I say? This inner Gaussian surface, it does not contain the entire charge. It only contains a proportion of the charge which is enclosed by the small radius r. So this becomes q r cube over r cube. Now let's get started. So this is, I'm sorry, I have to put an electric field here. So the left hand side is E is equal to q r cube over 4 pi small r square epsilon 0 r cube. Okay. Now this upstairs and downstairs, the r gets cancelled. So you have this electric field for the point, at a point where the small r is lesser than capital R. The electric field is q times small r divided by 4 pi epsilon 0 capital R cube. So this is the result. Now this is very interesting for all those points which is inside the sphere. You have this electric field increasing linearly with r, but for all those points far away, you have the electric field varying with 1 by r square with the distance. So we can make a plot. So this plot is going to be like this, and this is going to be your electric field, and this is going to be the radius, whatever it is. This is capital R, which is the radius of the sphere which is charged, Now inside the sphere, this electric field increases, proportional with r. Then once you have for all those points outside the sphere, E is proportional to 1 by r square. So this is a maximum what it can get, and that's nothing but kq by r square. So k is 1 by 4 pi epsilon 0. Suppose here at the surface, if small r equals capital R, then this will be equal to q over 4 pi epsilon 0 r square at the surface. This is the result at the surface, electric field at the surface of the sphere, which is the same, equivalent to kq over r square. So using Gauss's theorem or Gauss's law, now we are able to very easily calculate what is going to be the value of the electric field in the case of spherical symmetry. Now let's consider another example. Now let's consider infinite sheet of charge. Infinite sheet of charge. Let's assume that the sheet what we have is non-conducting. Now it's like, very good example is, imagine that you are working with your blackboard and that's your infinite sheet of charge. So let's say it's positively charged. So this is how the charge is. Okay. Now we need to evaluate the electric field somewhere here. So we are going to calculate what's going to be the electric field here. So we need to construct a Gaussian surface. Now, well, if you go by the familiar example, and if you start thinking that a sphere is going to be a Gaussian surface, we are going to end up in troubled waters. So this is going to have a cylindrical symmetry. So this is going to be a Gaussian surface. Now this Gaussian surface is going to extend on both sides of this infinite sheet of charge. Okay. Oops. So this is how it appears to be. Now the electric field is pointing in this direction. Electric field is pointing in this direction, and this is the flat end of this cylinder. So this is your flat end. We don't have any contribution here for electric field at the corner. So we don't have any electric field here, primarily due to the fact that the electric field and the area vector, they are not parallel, they are perpendicular in fact. Now here the electric field and the area vector are perfectly parallel with each other, so we can take care of the dot product. But mind you, you have a similar flat end over here, this particular point. So here too the electric field and the area vector are in alignment with each other, so the electric field is pointing in this direction, the area vector is also pointing in the same direction. So we have two ends having almost giving us the same results. So that's going to be EA plus EA. So I have avoided a lot of steps. So ultimately the formula is integral E dot dA is equal to enclosed charge over epsilon 0. So here this is EA plus EA, that gives you 2 EA. As far as the right hand side is concerned, it's not so difficult, but here since it is a surface, we need to consider the surface charge density, which is sigma. Surface charge density, which is sigma, and sigma is nothing but Q times Q over area. And here instead of the charge enclosed, we can substitute sigma multiplied by A divided by epsilon 0. A goes off and the electric field is given by the relation sigma over 2 epsilon 0. So this is the electric field what has been evaluated for an infinite sheet of charge. Now, using Gauss's law, we can easily evaluate electric fields for surfaces having symmetric charge distribution. Now, let's say that you have an infinite line of charge. So this line is charged something like this, and then you have the electric field which is pointing out in this direction. So this is the direction of the electric field. Okay. Okay. Now let's choose our Gaussian surface. So once again, the Gaussian surface is going to be cylindrical. It's going to be like this. So this is going to be our Gaussian surface. So let's change the color of our pen. Okay. Now here, the electric field and the area vector here, they are parallel to each other, you can see. But however, here there is no flux coming out at the ends. So you don't have any flux coming out, electric flux at the ends. Once again, what can I say? The linear, charge density is lambda, and this, what can I say? The lambda is equal to Q over L, that is the length. So this is your length of this particular cylinder. Okay, fine. Now, what we have to do is we have to evaluate the left hand side. So the left hand side, once again, let us write the Gauss's law for convenience. E dot dA is equal to Q enclosed by epsilon 0. Okay, now let's get started with the left hand side. E is always uniform, so we can take that, and this is going to be dA, and this dA is nothing but the circumference multiplied by the length. So you can simply write this as 2 pi RL. Suppose if you spread out this Gaussian surface, it's going to be a rectangle, and this is what you're going to get, and this will be lambda L over epsilon 0. So this L goes off, and the electric field is lambda divided by 2 pi epsilon 0 R. So we have very easily evaluated the electric field for a spherical symmetry, planar symmetry, and a line of symmetry using Gauss's law. So Gauss's law is very convenient for us to evaluate electric fields easily. Okay, so that's all we have for this particular session, and in the next class, we will come up with some new concepts. Until then, have a great weekend. Enjoy yourself. Thank you.